Good morning and welcome to the second session of the 2009 Wagner competition. We have two presentations in this session. The Wagner Prize is sponsored by the Informs Practice section. The prize was established in memory of the late Dr. Wagner. There are 5 finalists presenting today in this session. They will be judged on success in practice, quality and coherence of analysis and solution originality, quality and clarity of writing of their papers, quality and clarity of oral presentation. As a background to the prize, a brief introduction to Dr. Wagner. Dan Wagner earned his PhD in mathematics from Brown University. Upon graduation, he joined the Navy's Operations Evaluation Group at the Pentagon, working on operations research for naval warfare until 1956. After 1 year as a postdoc researcher at MIT, Dr. Wagner joined Burroughs Research Center, where he directed a group of mathematicians performing analysis for development of digital computers. In 1963, Dr. Wagner formed a new company, Daniel H. Wagner Associates Incorporated. During his years as president and principal owner, Dan brought many high-quality mathematicians to the operations research community. This led to significant advances in mathematics for naval tactics, especially anti-submarine warfare, detection theory, and search planning. Wagner Associates delivered significant applications to the Navy, Coast Guard, and other clients, many of which applications are still in use today. After retirement from the firm, he founded Dr. Wagner continued his commitment to the field of OR, serving in various research and teaching positions with the U.S. Naval Postgraduate School and the U.S. Naval Academy. He was an active member of Informs, prior to that ORSA, for more than 40 years. That's incredible service. The idea for the Wagner Prize began at Dan's memorial service, where many of his former colleagues gathered. The prize is made possible by generous endowments from the firms Metron Incorporated, the Daniel H. Wagner Associates Incorporated, and Applied Mathematics Incorporated. I'd like to introduce the members of the 2019 Prize Committee. The judges, they are Bill Browning, Alan Butner, Larry Stone, Margaret Braundaughter, Brian Eck, Pavitra Harsha, Kanketur Siaglu, Eva Regnier, Emily Tucker, and myself. I'm Mary Hellender, the chair of the committee. Now for our presentations. The next presentation up, this is the 4th one today, is to be delivered by a team led by Xiaojia, and she's from the University College at London. Her talk will be London Heathrow Airport uses real-time analytics for improving operations.
Okay, good morning. Thank you, Mary, for introducing me, and thank you all for coming to this presentation. My name is Xiaojia Guo. I'm currently a PhD student at UCL School of Management, University College London. So today I'm going to talk about our work with London Heathrow Airport on developing a new system to predict the transfer passengers' movement in the airport. So this is joint work with Professor Bert Reyck and also Professor Yael Grushka-Cockayne from Harvard Business School. So let me first give you some background information about this project. So this project was sponsored by Eurocontrol, a central organization for air traffic management in Europe. So Eurocontrol was founded in 1960s, and right now it has roughly 40 member states. So our project was part of the Euro Commission's and Eurocontrol's single European sky air traffic management research project. So this project started from 2004, and 2014 was kind of an important milestone for this project because that's the start of the deployment phase of this CSR project. So one of the key deliveries of this CSAR project is the airport collaborative decision-making system. So to realize this collaborative decision system and to realize the idea of airport collaborative decision-making, airport operation centers have been developed by major European airports since 2014. So right now, the Airport Operations Center becomes the nerve center for airport operations. So these are some pictures we took from Heathrow. Basically, you have a physical room, and almost all airport stakeholders stay in this one single room and kind of have a single view of what's going on and the performance of the airport. So when we started the project, the system there was highly fragmented. It's like different stakeholders has different kind of data system, different format. Our project is a big data project, so we aim to emphasize the need to have a uniform data systems, and we also want to provide some kind of update to their decision-making system. Here are some information about the magnitude of Heathrow Airport. So Heathrow Airport is the largest and busiest airport in Europe. It carries about 18 million passengers to over 200 destinations per year. And among these 18 million passengers, about 24 million of them are actually transfer passengers. It is very expensive to run Heathrow. So they have 6,500 employees, and every year it costs $1.5 billion to run the airport. Heathrow's Airport Operations Center, the APOC, went live in 2014. And right now, arguably, Heathrow's APOC is the most advanced APOC in Europe. So throughout this project, we followed the 9-stage approach we developed here. Basically, first we work with Heathrow, we interviewed the managers, we reviewed the decision-making process in the center, and also the data flow in the center, and we identify key processes that can be enhanced by data and by advanced analytics. And then we consolidate the data, clean the data, we train a model, we test the model, we summarize key results, and finally we implement this method at Heathrow. As a first step, we interviewed many managers, almost all the managers in the center, and then we ask questions like, what kind of information you don't have right now, but you think that could be very important to you? Almost all the managers mentioned about transfer passengers. So here are some examples. A security flow manager who is responsible for generating some initial resourcing plans the day before operation, and then during the day of operation, they need to make some real-time adjustments to their resource plan. They mentioned that they don't have any real-time predictions for transfer passenger flow. So they always just look at the CCTV camera. And oftentimes when they realize there's going to be a congestion, it's already too late to make any changes to their plan. So here are two figures. The photo on the top is what we want to see. It's like everyone's happy with smiling faces, travel on time. But the picture on the bottom is the reality. You always end up in long lines and can't make your connections, and so basically passengers are not satisfied. Another example is the passenger flow manager, whose objective is to maximize passengers' experience in the airport. So they mentioned that they need some individual level predictions. I need to know who among these passengers are going to be late, so I can provide some support for them and help them make the connection. So after the interviews, we decided to focus on the transfer passenger journey in the airport. And then we further narrowed down our study to the international arriving passengers traveling through Heathrow's Terminal 5. This is the transfer journey at Heathrow, and it's very similar to all the international hubs in the world. So basically, passengers arrive at the airport, they disembark from the aircraft. Some passengers need to take a shuttle bus to Terminal 5. Then at Terminal 5, all the passengers need to go through the so-called airline's conformance desk. You need to scan your boarding pass there, then the airline will check if you are in the right terminal and if you have enough time to make your connection. After that, some passengers need to go through border force, and then all of them need to go through transfer security checking, and then you enter the retail and lounge area, and you move toward your boarding gate. We realized that there's a lot of decisions made at airline's conformance desk. So first, the airline will decide if the passenger is late or not at this point. So basically, you arrive here later than 30 minutes before your outbound flight's departure time, the airline will directly send you to some rebooking desk for assistance. And also the aggregate level prediction here, like how many passengers are expected to show up in this area, say every 15 minutes, those kind of information is very useful for making security and immigration resourcing plans. So based on these interviews and our identification of the problem, we decide to build a predictive system. So this predictive system has two phases. In the first phase, we predict some individual level, we generate some individual level predictions. We predict the distribution of the connection times between a passenger's arrival at the airport and their arrivals at the airline's conformance desk. So based on these distributions, we can easily calculate the probability of a passenger being late, and then we identify late passengers. We can expedite their journey through the airport. In the second phase, we aggregate these predictions from the first phase, and we generate some aggregate level predictions. The passenger flow or number of passengers arriving at this area in every 15 minutes. So basically in the literature, these two prediction tasks are usually considered as independent problems. Identify late passengers, that's 0 or 1 classification problem, late or not, 0 or 1. So people usually use classification models to identify late passengers. And for number of passenger arrivals, that's a time series. So usually time series models like ARIMA, exponential smoothing, are used to predict passenger arrivals. So what did Heathrow do before our study? Basically, there's no prediction about passengers' connection times. The decisions were made based on managers' experience. It's like, I think this passenger will be late, then I will provide some help. For prediction task 2, they use some kind of very naive time series model. Then in this approach, in our approach, in the two-phase approach, the prediction, the outcome from the first phase served as the input to the second phase. So basically, we generate the prediction of the connection times, and then we use those distributions to generate the passenger flow. Our study is also the first to use real-time data to forecast the passenger movements at an airport. Okay, now we have identified our problem. The next step, we collected data. So our data was consolidated from 3 data sets. 2 of them were provided by the airport, and 1 of them was provided by airline. The resulting data set has 3.7 million passenger records and 30 variables. So we have some flight level information. We also have passenger level information, such as passenger's travel class and origin airport. The next step, we work with Heathrow, and we created some new variables based on Heathrow's domain knowledge. The first one, here are just some examples of these variables. The first one, hour of the day the arrival flight lands at the airport. So this feature basically measures the business of the airport. If you arrive during rush hour, you may need more time to make your connection. Perceived connection time, this is a very interesting one. We define this variable as the outbound flight's scheduled departure time minus the inbound flight's on-track time. So basically, this feature measures the stress level, the passenger's stress level to trying to make the connections. Like, if you think you don't have enough time, you may skip a lot of things and then go to the conformance desk directly. Punctuality of the arrival flight origin and connecting flight destination, and finally arrival flight load factor and connecting flights load factor. This basically measures how crowded the aircraft is. If you arrive in a very crowded aircraft, you may need more time to disembark from the aircraft. So in the first phase, to predict individual connection times, we use a regression tree model. So regression tree model is very intuitive. You can always print out the regression tree and to see why a passenger's connection time is predicted in a certain way. So regression tree model has been widely used to generate point forecast. Here, we generalize the method to also produce distributional forecast. Basically, regression tree will partition passengers into different categories, and then in each category, you will have certain number of connection times. We use a smoothed version of the empirical distribution for this connection time as the distribution distributional forecast of passengers' connection time. We tuned the model using a 5-fold cross-validation approach, and then the final model partitions passengers into more than 2,500 categories. So the regression tree method helps us with the first prediction task. In the second phase, the number of passenger arrivals is the summation of several Bernoulli variables. So each variable represents whether or not a passenger will arrive during this interval or not. And the probability of a passenger arriving in this time interval comes from the first phase prediction, the distribution of their connection time. Then we show that in theory, the mean of the prediction for number of passenger arrivals is unbiased, meaning in long run, your expected error is 0. And we also show that the distributional forecast could be well calibrated, or your prediction interval has the correct coverage rate by adding some correlations between passengers' arrivals. So adding correlations between passengers' arrivals also intuitively makes sense, because not everyone travel independently in the airport. If you travel in a group, your connection time might be highly correlated, even identical. But technically, we can only assign passengers onto the same flight. We don't have group information. So here we make some assumptions. We assume connection times of passengers arriving from the same flight are correlated, and we assume that each pair of correlated passengers have the same correlation coefficient. And then this correlation coefficient becomes a tuning parameter in our system. Okay, here are some accuracy results of our model. We tested the point forecast accuracy using the root mean squared error, and then we test the distributional forecast. We use several quantiles here, the 5%, 25%, 50% until 90% quantiles to test the distributional forecast. We use the pinball loss. It's a very widely used measure to measure a distributional forecast. We also use hit rate to measure the prediction intervals. So here for prediction task 1, we compare our model with 4 leading machine learning methods to generate quantile forecasts. And then in the second phase, we compare our two-phased model with 2 traditional time series models, the T-Best model and Sarima model with covariance. We also compare with the two-phased model using linear regression as the first phase model. And in this figure, plus sign means our method is better, and minus sign means the other method is better. So as you can see from the table, our method performs better than the others in almost all places. So here is an example of the passenger flow on a test day in 2015. We have our developed model versus the traditional time series model. The blue dashed line shows the actual flow, and then we have the predicted mean, we have the 90% prediction interval. So based on these 2 figures, you can see our model is much more accurate than the traditional time series model. We also summarize some key factors on predicting passengers' connection times. So the first one, arriving terminal 5 or others, because we only consider passengers connecting through terminal 5. So if you arrive at terminal 5, you don't need to take the bus for transfer. So of course, you will take shorter time to make your connection. And then arrival flight origin, European countries or others. If you arrive from a European country, we assume that, and it is true that European airports have very similar layout. So these passengers might be more familiar with the layout of the airport, and they may need shorter connection times. Passenger travel class, economy or others. Business class passengers sit in the front of the aircraft. They can disembark first. And perceived connection time, I've already explained this one. The hour of the day that basically you arrive during rush hour or not. So after building this model, we implement this model at Heathrow. We do some live trials, and we developed an application for Heathrow to use this model in real time. So here is the interface of the application. Basically, the managers can set up several parameters, like forecasting window, number of simulations they want to run, and then we have several outputs here. The first output is the individual level prediction. So basically here we have each passenger, and then we have several quantiles of their connection times. And most importantly, the last column in that table is the probability of this passenger being late. So if you are expected to be late, like 90% or 80%, then the airport will help you to make your connection. The next output is the aggregate level prediction. So here, each row represents a 50 minutes time interval, and then we have several quantiles for the passenger flow arriving at the security and immigration area. We also group these predictions based on the outbound flight. It's like in the last table there, we show how many passengers are expected to be late for each outbound flight. And then we show that based on current scheduled departure time, you will have 3 passengers late. And then if you delay your departure time by 5 minutes, you'll have 2 passengers late. 10 minutes, 2 passengers will still be late. So our predictive system has been integrated in Heathrow's dynamic model of operation system. So there, right now, there's a connection at risk table, shows highlights all the passengers with high probability of being late. There's also a transfer security flow table, basically shows all the quantiles of the passenger flow prediction. And right now, the model is retrained every day, and the predictions is updated every 15 minutes. Okay, finally, these are some comments and some long-term impacts given by Eurocontrol and by Heathrow. So I'll stop at this page, and thank you for listening. I'm ready to take any questions. Thank you.
How about this? That's better, okay. So your predictions are better here, but have these predictions produced better performance, better operational performance, like reduced number of passengers that missed their flight or reduced lines for security? So
I think based on these comments, Heathrow did the evaluation. We didn't did the evaluation, but based on their feedback, we did reduce we reduced both cost and passenger delays.
Quantitative measures of that? Do you have quantitative measures of that improvement?
I think it's 24% of the cost improvement. 24% less cost for them. Their decision-making problem is essentially like a news window problem. That's why we have these quantiles. So in their decision-making problem, they have a understaffing cost, and they have a cost for staffing. So they said there's about 24% improvement using our prediction.
Judges, another question?
I actually have 3 questions. Is that okay?
There's one.
So can you just quickly summarize what actions are taking when you say 24% cost reduction? What's the total set of actions they are taking based on this work? So that's one question.
So first of all, I think passengers' experience is improved, because now, I don't know if you recognize that, notified that at the airport, they usually drive that little car to pick up passengers. So now they can better identify late passengers. They can pick up the right passengers and help them make their connections. This is one action they are trying to do now, based on our better prediction. And also, I think they have better resourcing plans right now, based on more accurate forecast. Because before our study, they only monitor passengers with a CCTV camera. So whenever they realize there's a congestion, they will adjust their resource. But it usually takes like 15 minutes to adjust resource. If they don't have the prediction, they can't adjust resource like in time. So right now, because they have these predictions in advance, they can better deploy their resource now. So that's how they reduce their cost.
You're calculating the total number of arrivals at immigration office, but in reality, if you want to calculate the total delay at the immigration office to the next flight, you need almost like a queuing system where the arrivals are coming in and there's a certain service rate and so on and so forth. It doesn't look like this is in your scope, so how are you even estimating the time to get to the next flight? Is somebody else doing it?
That's a very good question. At Heathrow, they have some estimations of serving time, and I think their current model is a queuing model. They use a queuing model to decide the resource level, but we are not doing the decision-making problem here.
Okay. So my last question is about the quantile loss, because I deal with that thing on my everyday life also. So there are two things that are important about quantile loss. One is not quantile loss, but when you're estimating a distribution. One is how well are you getting the quantiles, in which case quantile loss can tell you. But equally importantly, how narrow the distribution is. Yes. So the question is, what's the? So did you look at the performance of your P95 or Q95 versus Q50 versus the other models? How wide was your estimate versus how wide was the estimate from the other models? Did you look at that?
Yes, that's a very good question. So here we use hit rate to measure the prediction interval. It's like a coverage rate. The percentage of realizations falling into the prediction interval. So basically, if you produce 50% prediction interval, this hit rate should be 50%. We tested on that, and our model is better than the others.
All right, thank you.
Any other questions from judges? Eva, anyone? Can open it up to the floor. If there are any questions from the floor.
Have you done any stress test of your method? There could be a lot of disruptions in the system which could impact the arrival of customers, and there could also be cascading of these delays from one section to the other section of the system. So have you done any stress test of your algorithm to see how it performs?
So I think for our project, we focus on predictive analytics. We didn't do that, but I think that's a very good point. I think Heathrow should do that in their decision making.
We have time for one more question.
I wonder if you could just speak to the degree of implementation. It's not quite clear whether it's been thoroughly implemented, partially implemented, has the potential to be implemented. If you could speak to that, please.
The predictive system has been fully implemented. So basically, now the managers are actually using this application, and then they look at these outputs in their daily decision making. And these outputs also serve as input to their decision support system. So yeah, it's fully implemented right now.
Let's thank the speaker. Thank you. Okay, our fifth speaker today leads a team from DD Research America and also DD Beijing. It's Tony Quinn, and he will speak on ride-hailing order dispatching on DD via reinforcement learning.
Hi, good morning. I'm Tony Chin from DD Labs. It's a great honor to be selected by the Wagner Prize Committee for the final and to present our work on reinforcement learning for ride-hailing order dispatching at DD via a reinforcement learning framework. This is a joint work with a number of people. Xiaojia and Yael are also with DD Labs in Mountain View in California. Fan, Zhe, Hongtu, and Jiping are all based in the Beijing headquarters. And there are many others from the AI labs and marketplace teams who have contributed to the works here in one way or another. Online ride-hailing or mobility on demand has emerged only several years ago, but has already gained incredible popularity and prevalence around the world. This is all because the needs of travelers are shifting, with the current trends emphasizing the need for alternative forms of transportation and demand for more personal choice in mobility, according to the MOD fact sheet by the Department of Transportation. As we can see here, in the two largest markets in the world, urban population is approaching 82% in the US and 58% in China in 2019. People are increasingly relying on crowdsourced mobility supply through ride-hailing platforms to meet their travel demand, in addition to traditional forms of transportation. Now, according to data from Statistica, the top 5 ride-hailing markets around the world account for a total volume of about $130 billion in 2019, with China, the US, and India being the distant leaders. And we have seen emergence of a group of online leading players in this domain, with Didi headquartered in China, Uber and Lyft in the US, Ola from India, Bolt in the UK, and in Brazil, we've also got 99, which is actually not part of Didi. Some of you might not be familiar with Didi, the company, so I'm going to give you a quick overview of Didi's business and operations through a quick set of statistics. The lineup of our products include Express and Premier rideshare services, enterprise solutions, the traditional form of taxi, designated driving, bike share, and many others. Our platform supports over 550 million passengers, fulfilling over 10 billion rides each year. Now, to put the scale of data into context, each day there are tens of billions of location points and routing requests queried, and hundreds to thousands of terabytes of data generated and processed. The rideshare partnership that we have cover 80% of the world's population that reach more than 1,000 cities. Trip requests and vacant vehicles are matched, and transactions are completed within the ride-hailing marketplace. This is a two-sided marketplace where both the drivers and passengers are important players within the marketplace. To the drivers, the income and their idle time or their utilization is something obviously something that they pay much attention to. And to the passengers, their ridership experience is mostly reflected in the pickup distance, the order response rate, as well as the fulfillment rate. So as a platform, the ride-hailing system cares about all these matrices and try to optimize them through a set of levers, mainly the order dispatching, driver repositioning, as well as pricing. We'll focus on order dispatching, which is sometimes also referred to as order matching. The process starts from the potential passenger keying the origin and destination into the app. The platform then offers a quote for each applicable product. So here in this case, I select the Express product and submit my order. Then this is where the matching process begins. The system then searches for a vacant driver nearby to match my order. Now, upon the successful search, then my order is assigned to the driver, and I'm told about how far the driver is from my current location. If the search takes too long likely because of low supply, then I may drop my request. Likewise, if I see that it's going to take too long for the driver to come and pick me up, then I'm also gonna cancel my order. So this all seems to be quite straightforward, but why is order dispatching important from the system's perspective? Now let's look at two motivating examples. On the left-hand side, we've got one passenger and two vacant vehicles, one in cold area and the other one in hot area. So assigning the vehicle in cold area to the trip actually helped to reduce the overall idle time or for the interest of a total driver income, because the vehicle in the hot area is more likely to be assigned to another trip in the very near future anyway. Now on the right-hand side, the system has a choice to assigning the vehicle to either passenger. And here, apparently assigning the driver to the trip that goes to the hot area presents a better choice from the long-term perspective of increasing the total driver income. So we see that from this example that it's important to consider the long-run effect of our decision, because our immediate actions will affect the future outcome. The optimization problem that we are interested in solving is a dynamic problem, in that the trip requests stream in throughout the day, and the driver's availability is stochastic. They can get online and offline at will. And we would like to solve for an online dispatching or matching policy that matches drivers to passenger requests on the fly, with the objective of improving the overall marketplace efficiency. That is, higher total drivers' income, higher order fulfillment and response rates, and shorter pickup distance. Our solution framework is based on reinforcement learning, and specifically the generalized policy iteration. Here we start with a given matching policy, and we collect order transaction data under this policy. We then learn the value function from the data using a policy evaluation method powered by a deep value network that's tailored for spatial temporal applications. Now, based on the value function, then we generate a new order matching policy by supply-demand batching and solving a linear assignment problem with the assignment edges defined by the output of the value function. And since we support a large number of cities, then transfer learning is also important. So the deep value network also facilitates the transfer learning to transfer knowledge from the information learned from one city to other cities, so as to make the training of the models for all of the cities better and faster. Now, let's put the problem into mathematical terms. Our goal is to solve for a system policy, pi, which assigns an order to one of the drivers, one of the free drivers at the assignment time. And the set of free drivers x of t depends on the matched trips before t and the policy pi itself. We set the price p of pi to be 0 if the order is canceled before fulfilled. And the objective that we consider in this talk, the primary objective we consider in this talk, is the total driver income. That is the sum of p of pi over all the submitted orders. And we can define the other matrices of interest accordingly. For example, the average pickup distance, the response rate, and fulfillment rate. A common approach to optimize order dispatching under the dynamic nature of demand supply is to batch trick requests and drivers within predefined time windows and solve the matching problem at the end of the batch window. Matching is then formulated as a linear assignment problem, which can be solved by the KIM algorithm, aka the Hungarian method. The W's here are the edge weights for the assignment problem, and the Z's are the pairing decision variables. The edge weights could be as simple as the within batch on raw time or the pickup distance to minimize the overall pickup time within the batch for the orders within the batch. And we treat this mathematical program as a policy generator with the inputs of the W's, the edge weights, and the output is the decision variable Z, which can be translated into the system policy pi. So the combinatorial optimization approach is actually now an industry standard method, and that is also something that we start with. The linear assignment based on within batch pickup distance is myopic, however, in this case. And we have seen from the motivating examples that it's very important to look at the long run. So to do that, we model the trajectory of the driver by a semi-Markov decision process. Specifically, the state of the driver is a cell in the discretized spatial temporal grid. So here's an illustration of a spatial grid map with hexagon cells. The option of a semi-MDP is similar to an action in an MDP framework. And it's to either serve a particular order or to idle cruise. And the difference from the action in the MDP is that option lasts over multiple time units. The immediate reward here is simply the trip price, the income from the trip price, which is just a constant fraction of the total trip price for the driver. And the state transition of the driver is governed by the transition probabilities. And in this case, actually, the transitions are deterministic. And our semi-MDP is episodic. So the state of the driver reaches the terminal state when the time component is at the end of the day. Since the reward collected from the option is over multiple time units, we basically divide it into pieces and discount each piece properly while considering the en route time for the driver to pick up the passenger. The driver's policy is a function that maps the state to an open order. Since it's from the single agent perspective, it's actually dual to the system policy in that whenever the system assigns the order I to driver X, the implied policy for the driver X is to serve order I. The value function always associates with a particular driver policy pi d, and is the expected long-run cumulative income with proper discounts given the current state of the driver. To learn the value function from the set of historical data, we started out with a traditional policy evaluation method, the tabular TD learning method, temporal difference learning method here. The value function is represented by a table corresponding to the spatial temporal grid. It's iteratively updated in the DP manner by the difference between this one-step bootstrapped estimation of the origin's value and the actual value of the origin. Depending on whether the driver is in service or not during the transition, then we plug in the proper immediate reward into the updates. And once we learn the value function from this set of updates, we then compute the edge weights of the linear assignment problem through the temporal difference error on each eligible driver-passenger pair. So that is the sum of the immediate reward and the one-step bootstrap estimation, and taking the difference of that and the actual value of the destination. The policy learned in this way is a collective greedy policy that tries to optimize the income for all the drivers within the batch. And the objective here is obviously a sum of the cumulative reward for each individual drivers within the batch. The tabular policy evaluation method is simple to implement and works, in some cases, works quite well against distance-based assignment. However, there are three major limitations that call for more sophisticated representation of the value function and the training method to learn it. The tabular state representation is unable to capture the dynamic nature of supply-demand context within the grid. So additional contextual features are needed to enrich the state representation. But a tabular form of value function is intractable in terms of the number of features. Now, secondly, our data may not be able to cover the entire state space. So how is the value function going to generalize to states of the driver that have never been seen before? Principal generalization is hard to do on the tabular form value function. Since we support a large number of cities on the platform, it's also important to be able to leverage knowledge during training from one city to and the other cities. But a tabular form value function lacks the mechanism for transfer learning. So to tackle those limitations, we further develop a deep value network architecture to learn the value function. In addition to nonlinear function approximation and contextual features, our novel deep value network has a few technical highlights. For state representation, it takes advantage of a hierarchical grid system to learn an adaptive quantization of the location through grids of different sizes to capture unique geospatial properties. Each location is then represented by the sum of cerebral embeddings at different scales. These embeddings are memory-based neural networks and are learnable high-dimensional representations. For training of the value function, we have developed a regularization scheme that puts a penalty term of Lipschitz constant of the neural network to the square loss at each network update in the stochastic gradient descent. The Lipschitz constant is the upper bound of variation of the value function with respect to its input. So this makes sure that the new function is not too sensitive to the input perturbation. And this is important, especially in the case of a nonlinear function approximation, because bootstrapping is used in function updates, and training stability is sometimes the issue. Now, putting the deep value network into our generalized policy iteration framework, we obtain a practical two-stage iterative solution that comprises learning through deep reinforcement learning and planning through bipartite graph matching. The incorporation of long-term values in the assignment edge weights is through the temporal difference errors on the driver-passenger pairs. This is the same as in the TD learning case. Let's visualize the spatial temporal value function for a major city in China. These are the value heat maps at a time slice before the morning and evening rush hours. The contrast here is actually rather clear. the residential areas around the city center in the morning have higher values indicating that drivers there have a higher income prospect than others given under the given dispatching policy. Whereas the situation is reversed in the evening due to higher demand in the downtown area. For transfer learning of the models among different cities, we further refine our neural network into a dual pathway architecture where there are two trains of network layers corresponding to location features and transferable features such as the time, spatial temporal displacement, as well as local supply-demand contextual features. The two pathways are then connected through lateral connections. Once the network for the source city is trained, the green blocks, which are the transferable blocks of the network, is then transplanted into the network of the target city, which is then further trained by the new data from the target city. We have built a simulation environment for evaluating our policies and comparing benchmarks. This simulator has a combination of deterministic and dynamics and stochastic models. We have benchmarked the distance-based matching, tabular temporal difference learning, and our deep value networks in our simulation environment. And it's clear that the reinforcement learning-based methods outperform the baseline by 5 to 8% in total driver income, and the deep value network shows the best performance. We have also tested transfer learning scenarios with city A as a source city and the other cities as targets. Again, we see that our proposed transfer learning architecture strikes the best trade-off between total driver income and pickup distance. We deployed our solution to production to carry out an A/B test in 3 pilot cities over months of time last year. A/B testing order dispatching algorithm is actually not as straightforward as one would imagine, as in the case of testing recommendation systems. The main reason lies in the nature of a two-sided marketplace. The demand traffic is not separable with respect to the order dispatching policy without separating the supply. Now, without creating 2 production order dispatching systems, then we have to resort to alternatives to allow 2 order dispatching policies run in the same city with minimal interference. So here we use the time slice rotation, where the 2 order dispatching policies are executed alternatingly for periods of 3 hours within the day, and the order of execution is switched from day to day for an even number of days. So we carry out the A/B test, and we see that the reinforcement learning-based method also consistently outperformed the distance-based minimization baseline with a statistically significant margin in driver income as well as in the order response and fulfillment rates. Now, let's hear what Dr. Jieping Ye, VP and head of DDAI Labs, has to say about the real-world business impact of this project.
Hello everyone, I'm Jieping Ye, VP of DD Chuxing, head of DDAI Labs. Order dispatching is the process in a ride-sharing marketplace that has direct impact on both driver and the passenger experience. That's why here in DD, we invest significant resource in the research of order dispatching algorithms. In recent years, we have seen a steady rise in applications of reinforcement learning in solving complex sequential decision problems. The groundbreaking work in this presentation is precisely a very innovative way to combine reinforcement learning and operation research in a large-scale real-world system. The reinforcement learning research program for order dispatching is in its 3rd year, and we have seen a profound impact that it brings to DD marketplace. We have implemented the generalized policy iteration framework in production for over 20 cities in China and gaining a consistent improvement of up to 2% in order response rate, fulfillment rate, and the total driver income. The coverage and the impact of this work continue to expand over the nation, allowing hundreds of millions of passengers to enjoy a better travel experience. We believe this is the first successful industrial application of reinforcement learning-based method in the ride-sharing domain. This work has fundamentally revolutionized our approach to ride-sharing auto dispatching, dynamic resource allocation, and other operation research problems in industry. Thank you.
There seems to be a little bit glitch in transferring, the map-made video onto a Windows system, but let's go on. So there are several directions in the research for auto dispatching that we are currently pursuing and in the near future. The generalized policy iteration framework that I have just described has two separate stages. Now it's natural to see if an end-to-end deep reinforcement learning method would work in this case. Along the way, then we have to solve sample complexity and scalability issues and solve domain adaptation for deployment. We are also interested in viewing the ride-hailing marketplace as a multi-agent reinforcement learning environment to develop cooperative multi-agent strategies as well as hierarchical reinforcement learning methods. So that's it for today. I'll conclude here. Thank you.